Let's talk about line integrals. We'll talk a little bit about the notation, what they're doing with the calculating, and then we'll look at an example of a line integral over a vector field. So in Calc 1, what we did is we integrated a function along the x-axis, right? Most of our integrals were in terms of x. We're basically integrating along the x-axis. Gave us the area under the curve. Now, what we want to think about is we're going to integrate a surface along a path C in the xy plane. Okay, so imagine you have your xy plane and you have some curve being traced out. A line integral will give you the area under that curve above the xy plane. Does that make sense? Now, that's not how we're going to use it, but that's one thing that the line integral will give you, and that's how it's related to Calc 1. So that's a line integral over a function. So suppose we have some function, we'll call it f of xy, and we're doing it along some curve C that's given by the position vector, x of t, y of t. Then the line integral of a function is the function multiplied by the magnitude of the displacement vector, which, if we write out what the magnitude of the displacement vector is, it's the square root of x prime of t squared plus y prime of t squared. All right. One thing I want to point out now, and I'll bring this up again later, a line integral is actually just an integral of a single variable. That's not why we're not seeing the double integral up front, because what we have are parametric equations for our curve. And we're going to be doing that a lot in this, especially in this first section, is parameterizing the curve, and that will make our line integral of one variable. We'll look at some double integrals for line integrals in Green's theorem next week. But a line integral itself typically is just a single variable integral. So setting it up is the big thing. Once you have it set up, you have basically a Calc 1 problem. Something important I want you to notice, if the function, this function here, were set to 1, then really all we have is arc length. So that would just, so basically what we're doing is we're integrating a function over the length of the arc. So if our function was density, then what we would be measuring is the total mass of that rod or a wire that goes along the curve. So these are actually, I think you're going to find easy to do, because all we have to do are two things. If we don't already have the parameterization for the curve, we might have to find the parameterization. But if we have the parameterization, all we do is plug in what x and y are in terms of t into our function. And then we find the derivative of x and y, and those go into the arc length portion of the line integral. It's actually a really straightforward process. Now, yes, if our parameterization is really messy or our function is really messy, we might get a messy integral, but setting it up is just a matter of substituting into the formula. And we're going to try one of those when we go to the worksheet. What we'll see more often is going to be a line integral over a vector field. All right. So if you think about that Gulf Stream, when we first looked at vector fields, we talked about, hey, if we go along with a flow line, if we drop a bobber in the water, we just watch it kind of go along with the flow line, that creates the flow line through our vector field. But what if something is traveling through the water on its own path, not necessarily along with the flow of the water? Okay. A boat, some kind of object, an animal that's maybe swimming across the Gulf Stream. So a line integral over a vector field determines to what extent our path along a curve is going with the vector field or against the vector field. All right. So again, a boat in the Gulf Stream, right? We might want to know to what extent it's going to go with the flow of the Gulf Stream and what extent it's going to go against it, because that may determine, how much we need to accelerate the engine, right? Just kind of giving you an intuitive sense of these. Also, there's a couple links. They were in the course content folder, but I didn't have them linked on the calendar, and I linked those up today. So kind of talks about a line integral of a scalar function, which is what we just talked about, and an intuitive sense of a line integral over a vector field. They're by Maths Insight, but very similar to that Better Explained website. Just give you kind of an intuitive sense of what the heck it is we're looking at. Now, in order for us to do these, we have to have what's called an oriented curve, meaning it has to have a direction. All right. Now, again, you can imagine a boat going through the water. It's going to be going in a specific direction. So one of the things that we'll talk about as we go along these curves is what direction are we heading, because that makes a difference in our line integral. We talked a little bit last time about path independence and path dependence, which we're going to talk more about on Thursday when we look at the fundamental theorem of line integrals. But that path that we're talking about being dependent or independent, that's this curve that we're talking about now. We're moving along a curve. That's the path that is dependent or independent of our vector field. So we won't be talking about the conservative and non-conservative vector fields today. We're not worrying about that today. We're just getting this idea of a line integral down. But on Thursday, it's going to be a big idea. Okay, so here's what makes up a line integral. We have a vector field and some oriented curve going through the vector field. Well, so what we do is we approximate our curve with a bunch of little straight line segments along which f is approximately constant. All right, this is the same idea as a Riemann sum. We break it up so it's small enough so we can assume the vector field is constant. And then we want to know to what extent does the vector field go with our direction of motion or our path. Well, that should bring up a concept we talked about actually a little while ago. It's been a while now, but the dot product. The dot product for vector projection tells us to what extent one vector is in the direction of another. So we find the dot product on each of these little broken up segments, and then we add them up with a Riemann sum to get the total. Then when we take infinitely many intervals, we get our definite integral. So you're going to see me write this form a lot for line integrals, f.dr. And we'll talk about what each of these mean and how we can calculate them here shortly, over a path C. So once again, it is a single integral because we're going to have a parameterization for our path through the vector field. So everything is going to be a function of t or whatever we're using for our parameter. So just to bring that notation back up. Okay. So as we're starting to wrap our heads around it, one way of thinking about this, if our vector field is a force field, gravity or something like that, then what the line integral gives us is the amount of work done by the field as the object moves along the path. Since the integral uses a dot product, if the path is in the same direction as the vector field, it would be positive. If they are in opposite directions, negative. And if they're perpendicular, remember that the dot product gives us 0. Okay. And what it does, and what's happening is the integral will sum up all these dot products for us and give us some number that might be positive, which means our path of motion is more in the direction of the vector field. Could be negative, which tells us our path is more opposite or more against the vector field. Or we could get 0, which could mean one of two things. One, it could mean we have a constant vector field and our path is perpendicular. But more than likely, what it means is we're going with the vector field as much as we're going against it. So the positive and negative kind of just equal each other out. Now, I'm going to show you a notation for line integrals that I don't want you to worry about too much because I don't think it's going to be too useful in most cases. There are cases where this is useful. So we have our position vector, and x and y are functions of t. But right now, we'll just say, okay, it's in terms of x, it's in terms of y. And then f has two components that could be functions of x or y. So if we dot those together, we get p of xy dx plus q of xy dy. The reason I say this is not necessarily all that useful is if p is a function of x and y, this first integral can't be done. Similar argument for this one. So this is only useful if p of xy is a function of x or a constant, and q of xy is a function of y and a constant. So more often than not, we'll be parameterizing. But we could generalize this into 3 space. So everything we're going to do generalizes into 3 space. It just gives you that third component. Like I said, more often than not, I'm going to be going back to this form, f dot dr. Okay. F of r is our vector field with our parameterization put in. Dr is basically the derivative of our position vector, which is our parameterization. All right. That's a whole bunch of words right now. It'll make more sense here when we look at an example. So if C is our oriented curve given by the parameterization x of t, y of t, then dr is x prime of t dt, y prime of t dt. Sweet. We might have to move a little. Thank you. That doesn't happen in a long time. 3 space. It's the same basic idea that r prime of t is going to be x prime of t, y prime of t, z prime of t. Okay, let's put all this stuff together. This is going to be the form we see more often than not. Like I said, a lot of times I'll just write f dot dr for shorthand. This is what's going on. So here's what it would look like all written out. All right, great. What does that mean? Well, let me show you. So we're going to take this guy and we are going to set it up. It doesn't make for a super nice integral. So we'll have Symbolab calculate it for us. But let's talk about how these pieces that I just called through at you go together. All right, so we're calculating a line integral. And we're given the vector field negative y sine of x, cosine of x. And C is the parabola y equals x squared from 0, 0 to 2, 4. So the very first thing I want to do is I want to parameterize that curve. Okay. Well, anytime you're given a function, so if you're ever given your curve as y equals a function of x, your parameterization is actually pretty straightforward. What you do is C is going to be, you're going to let x equal t, and then y is going to equal t squared. And t is going to go from 0 to 2. And we can double check this. That makes x go from 0 to 2. And because y is t squared, it's going to go from 0 to 4. Right? So anytime you're given y as a function of x, the parameterization is very easy. So what we'll do is before we break up into groups, is I've got a couple that I want you to work on today. We're going to do the parameterizations together, but those are going to be things that you get better at as you get some practice. Some of the problems in the worksheet parameterization is given, and we won't worry about this. Okay, let's talk about what all this means. So again, first thing you need, a vector field and a parameterization for your curve, if it's not already given. Some of the problems, it'll be given. All right, we want to do the line integral of f dotted with dr. Okay, I'm not going to write out this part, but this is what comes next. So basically, if that's my c, then r, we'll put a t, is t comma t squared. Then dr, which is r prime of t, is 1 dt, 2t dt.
Kind of hard to see at home.
What's that?
Kind of hard to see at home.
Okay. The whole thing?
On the right,
Okay. What was that? R of t equals t comma t squared. Then dr is r prime of t, 1 dt, 2t dt. Or the way I like to write it is 1 comma 2t dt, because I can treat that dt like a scalar. So that's going to be the dr. It's just this piece here. The other thing that's in part of this is f, except with our parameterization plugged in. So what this is going to look like, so I'm going to take f, but I'm plugging this in terms of t. This is what makes this all a single variable integral. So negative t squared sine of t, comma, cosine of x is equal to t. This is going to get dotted with 1 comma 2t dt. Questions about where any of this is coming from? Like I said, it's just substitution. I took our vector field and I used our parameterization to get it in terms of t. And the dr is really just the derivative of our parameterization. So now, let's add one more part. We need limits on this thing. The limits come from the parameterization. There's no extra work we have to do there. It is automatically 0 to 2. Next comes the, oh yeah,
That's because of t, not because of x.
correct. I mean, x was involved in it because x is going from 0 to 2, but you're right. It's specifically this here, the limits on our parameterization.
X just happens to be the same thing.
Exactly. All right, dot product these together. So remember dot product, multiply these. So negative t squared sine of t times 1 plus 2t times cosine of t dt. We're now at a single variable integral that we can calculate. All right. Now, like I said, we're not going to do this one by hand because this would need to be split up into 2 integrals. And both of them would be integration by parts. This would take 2 rounds of integration by parts. This would take 1 round of integration by parts. Not terrible, but I just don't want to use the class time to do it. But let's take a look. There's two things I want to look at before we calculate this. So first off, let's just look at what's going on here. So here is our vector field, the negative y sine of x, cosine of x. So this is what our vector field looks like. Let's put in our parameterization. So to put in the parameterization, we're putting in a space curve. And this is where you would put in your parameterization. Just put in 0 for z because when you're in 2D. We could do these in 3D as well. So we have negative y sine x and oh, sorry, no, I'm putting in the parameterization. I already got the vector field in. Sorry, blank for a second there. This is just the parameterization that we did on the board. T squared, and we are specifically going from t equals 0 to 2. Okay, so there is our curve. And t is going from 0 to 2, so our orientation starts at 0, 0, and goes this way. As you can imagine, that will give us the opposite sign if we started here and went this way. So what we want to look at, we just want to get an idea of whether we think this answer is positive or negative. And remember what the vector, this integral gives us. To what extent does our path go against or with the vector field? And the larger the magnitude, the more powerful the vector field is. If it's perpendicular, it's 0. So if we look at this, okay, this one's clearly perpendicular. This one kind of goes with it, but it's a little small. This one's perpendicular. This one goes against it and is a little bit bigger. Against it, a little bit bigger. Against it, but also a little bit bigger, right? We're getting bigger as we get further away. So would you expect our line integral to be positive or negative or 0 based on what we're seeing here? Yeah, it seems like it's a little more against than with. You know, none of these are like really hard angled against it, but the size of these vectors here is much bigger than the size of the vectors that are with it. So let's just see if we get a positive or negative. We're going to revisit this one on Thursday because it turns out we can solve it very quickly with the fundamental theorem of line integrals by hand. Okay, so all I did was put it into Symbolab just to save some time. And we, in fact, get a negative number for cosine of 2. All right, so you guys keep track of that answer for next time because we're going to look at this one and see how we can by hand get 4 cosine of 2 without having to go through integration by parts. All right. Yeah, cosine of 2 comes out negative, which is makes the negative value, which is what we expected was a negative. All right. So we'll revisit this one once we have the tool of the fundamental theorem of line integrals. Okay, so that was the example I wanted to do with you. We should be able to keep that example up there, but we'll see. Only one last thing I would just want to say. Sorry, excellent. Back to the beginning. And that is, you know, we can look at this in 3 space. We're doing the same thing. It's just we're going to have a third component on our vector field and a third component on our parameterization. But we do the exact same thing. We dot product our vector field with our parameterization plugged in, dotted with dr, which is x prime, y prime, z prime. All right. Because if we have time, I'm going to have you do a 3-dimensional one too. It just adds on that extra component. Okay. Questions about that example? These are ones that I think once you get into, you're gonna feel pretty good about because they are straightforward to set up. Yes, you can get some messy integrals sometimes. Wolfram, Symbolab can take care of those. But setting them up is actually good. You're gonna find it is a pretty straightforward process. So here's what I want to do. I want to look at a couple of them from the worksheet I'm going to have you do. So I'm going to bring the worksheet up. All right, so you're going to do one of the ones from number 1. Don't worry about that right now. But I want to notice in 3 and 4, you're given the parameterization. You're given R of t. So to find dr is just the derivative of that. And all you do is plug t in for x, 4t in for y, t squared in for z into your vector field. So you got to try one of those. But 2 that I want you to try are number 2, d and e, where we do need to come up with a parameterization. And we are going to need some more space. So let me yeah, we'll take that and we'll turn. So I'm going to go use some of this board space over here. Okay, so first one, 2D. I'm gonna just give you guys, also give you guys the worksheet, so it's kind of small up there. So for 2D, our path is the right-hand side of the unit circle in a counterclockwise direction. That's so the whole half. So what would that look like? So we're going counterclockwise. Now, the reason I want to do this one with you guys is because we're going to see a circular path a lot, whether it's a whole circle or part of a circle, because it's just our trig functions. And our trig functions with x being cosine and y being sine do already go in a counterclockwise direction. There's a lot of ways to switch the direction. The easiest is to switch sine and cosine. Now, if you're not sure about, starting and ending at the right place, that's where you can use something like Calcplot 3D along with the space curve to make sure that you have a correct parameterization and correct limits. Okay. But for this one option, that's the other thing I want to do. I mentioned there's infinitely many options for parameterizing a curve. As long as your parameterization is correct, your final answer will be correct. It's up to you to decide, what parameterization you want to use. So if you want to keep this one kind of basic, so like x of t equals cosine of t, y of t equals sine of t, which again, that's our most basic parameterization for a unit circle, but we want the right half. So t is going to have to go from negative pi over 2 to pi over 2. Because if I do 0 to pi, I'm actually getting the top half. And depending on the vector field, there's absolutely no guarantee that the line integral is going to come out the same, because these vector fields don't have to be symmetric. Okay. So that's one parameterization you can use for that. Because I wanted you to be more focused on setting these up today and not worried as much about the parameterizations. You'll get practice on that in the homework. Okay. The other one is 4E, or excuse me, not 4E, 2E. So if we look at that one, now you've got a triangle joining 3 points. And there's a reason I want to have you guys do this one today, but I'm going to have you do it in a very specific way. So we're joining the points 1, 0, 0, 1, and -1, 0. And we're also just going in a counterclockwise direction. So we're kind of going this way. Because this is going to be one we revisit as well next week with Green's theorem. Now, when it's nice and smooth, we can represent it with a single function. When it's not, this is what we would call piecewise smooth because of the corners. We're going to have to represent each part of the path with its own set of parametric equations. Okay, so maybe we call it L1. Actually, let's use C1. C1, C2, and C3. All right, so this will actually be 3 separate line integrals, one for each, and then we'll add up the contribution of each at the end to see what we get. So on C1, because we're doing them all separately, we can always we can make T be whatever range we want. We can make these be whatever we want. Well, let's look at what's happening to go from this point to this point. X goes from 1 to 0, right? So it's actually going down. So maybe we do X equals 1 minus T. And this is going to be for T going from 0 to 1. So when T is at 0, X is 1. When T is at 1, X is at 0. This is also the graph of 1 minus X. Y-intercept at 1, slope of -1. Now what happens with Y? It goes from 0 to 1. So if T is going from 0 to 1, then Y is just T. So that would be the parameterization we could use. Again, a parameterization. So many options here. So C2, I'm just going to keep going from, starting at 0 because it makes it easy. And we're doing them separate anyways. So now what happens? Well, X goes from 0 to -1, right? So if we want to start at 0 again, what can we do here? We want X to go from 0 to -1. And if we want to, let's keep the same bounds. T is going to go from 0 to 1. What could be a parameterization for X? X we want to have go from 0 to -1 as T goes from 0 to 1.
0 minus T.
0 minus T. So,
X equals -T.
oops, I forgot the X equals, thank you. Perfect. X equals -T, right? So when T is 0, X is 0. When T is 1, X is -1. And 0 minus T, same thing. Now Y, what does it have to do? It has to go from 1 to 0. Yeah, we already dealt with that up here, right? So 1 minus T. So there's our parameterization for C2. Okay. Lastly, C3. Well, first off, one of the things about C3, Y is 0 the whole time. So and X has to go from -1 to 1. A couple different ways we can handle this. Here's one way. So we can let X equal T minus 1. And now, instead of going from 0 to 1, T is going to go from 0 to 2. Because we have to go all the way up to 1 on the X. We could also have made this, 2T minus 1 and gone from 0 to 1.
Would you have been able to do X equals T and just range it -1 to 1?
Absolutely. Yep. The only reason, my only reason for using 0 as the lower limit is I know these are going to be my limits of integration. So sometimes it's nice to have the lower one as 0. But to your point, that would absolutely work. If you guys didn't hear the question at home, it was, he asked, could you have done T and gone from -1 to 1? Absolutely. Yeah, infinitely amount of ways that do it, that'll work. So when you get to number 2, this is 2C or 2D, excuse me. You know, so I want you to try one of the ones from number 1 first. But then when you get to number 2, I want you to try 2D and 2E. Basically, you're going to, here are your parameterizations. You're going to do the exact same steps we did right here. Now, the other thing, and this goes for you guys at home too, I don't want you to do all 3 of these. We're going to split those up. So one person will do C1, one person will do C2, one person will do C3. And then we'll add up all the contributions at the end, so we don't get stuck on this one. Because if you have time, I'd like you to try either 3 or 4, so you can try a 3D one. Okay, any questions about what we got to do? All right, then let's try some line integrals. And I'll mute so we don't disturb you guys at home.